Now we are going to describe the basic physics and the basic description of our pulsating star systems. Many systems in nature are continuous systems where the concept of mass points does not longer hold. For instance, all fluid flows are continuous systems, even systems, and you cannot decompose them into mass points. And you have to think about one possibility. And if you think of, for instance, interstellar gas clouds, they are rather described by a gas, not by mass points. Or if you think of stars themselves, they should not be considered as point masses, but they have an extension and they have flows within their atmospheres, within their cores. And these flows are usually described by continuous fluid mechanics. So I was told that accept some basic concepts of fluid mechanics, which I will later on use for further description of the systems. So let us start how we could describe a continuous system. Continuous systems are composed of mass elements. You disentangle your flow or your configuration in a fluid or in a gas flow. The first one is due to Lagrange, and Lagrange considers a fixed mass element, and so to say, it always concentrates on one mass element and concentrates on the motion of this mass element within a continuous configuration. Without any restriction, you may say you label it with its initial position at time t equals 0. And you label it with R0 is the position vector of your mass element at time equal to 0. Well, in the course of time, the position of this mass element will change, it will move. So the actual position R at which the mass element will be after time t is a function of time, of course, and is a position of the initial position of the mass element at time t equals 0. So we can write the position of the mass element is a function of its initial position and time t. Of course, once we consider this as a transformation from R0, from the initial positions to the actual positions, we can also do the back transformation. We can ask, once we have a mass element at position R at time t, what was the position at time t equal to 0? This would be the inverse transformation, which determines the initial position vector from the actual position vector and time t. So this considers a fixed mass element. Well, then we can associate some quantities or some properties of this mass element. Let's call this property F related to the mass element and say, well, we consider a fixed mass element, then this quantity will also depend on the initial position vector and time t. And to make clear that we are in the Lagrangian picture, we label it with L. That means we have a property of this element. Could be pressure, it could be temperature, it could be density, or any other possibility. It depends. If we fix the mass element, it depends also on the initial position and time t. So to say the observer, once we are an observer, we are moving together with the element. It's the co-moving observer description. Okay. So in this case, uh, the independent variables are the initial position and time t, and the actual position r is a dependent variable. So it is you must keep this very well separate. The independent variable r is a dependent variable, and r0 and t are the independent variable, and r, the actual position, is a time dependent variable. This is one approach. An essentially equivalent approach was introduced by Euler. He considered the situation at a fixed point in space. So he considers the quantities, or let's see, a flowing across a fixed observer's position. Then you will have several mass elements traveling across your position. So in the course of time, the Eulerian observer will see different fluid elements passing his position. So it's a completely different point of view. So he sits at a fixed position in space, and the independent variable in that case is the fixed position in space and time t, rather than r naught and t. Now we will do the same as in the Lagrangian approach. We will associate some quantity to this position. So we will look for a property like temperature, mass, temperature, density, or pressure related to the position vector. So, and to make clear that we are talking about the Eulerian picture, this is a function, or is a quantity in the Eulerian picture, which depends on a fixed position and time t. So in this case, the observer is at some fixed point in space. The observer is at rest. Okay, how are these Eulerian quantities related to the Lagrangian quantities? Well, the Eulerian quantity must be equal at position r, must be equal to the Lagrangian quantity which the mass element has, which just passes the position r. Of course, the quantities have to be equal once we consider them in the different descriptions. But if we take the Eulerian quantity at position r, then this quantity in the Eulerian picture has to be equal to the Lagrangian counterpart of the fluid element which just passes the position r. So we have to do to see which is the element which is actually at position r. We have to determine by the back transformation from r to r0. We have to determine the initial position of that fluid element. Is that clear? Please object. Pardon? Yes. Okay. Well, you have a quantity f which is determined in the Eulerian scheme. Then it depends only on the position, on a position which you fix in space. Once, if you want to know what is the fluid element which is actually at this position, you have to determine what was the initial position of the fluid element which is just at the position r. So you have to determine where does it come from. Does it from which r0, from which initial position does it come? Is that okay? So, and then these quantities, the quantity f of in the Eulerian picture, of course, has to be equal, because we are referring to the position in one picture, to the position which we consider, and then we have determined the initial position of the fluid element that just travels around at this position. That's okay? It's a little, you have to think about it several times. Yes, you are at a fixed position and several mass elements travel along your position. Yes, yes. Yes, exactly. Yes, yes. You have to determine where it comes from, and then then the quantities have to be equal. Yeah, if you like to put it that way, it's fine. Yeah. Yes. 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 Exactly. Of R. Yes. Yeah. Yes, you have to use the back transformation to get where this fluid element comes from. Okay, and of course vice versa. If you look at the Lagrange at the quantity f in the Lagrangian picture, which depends on R naught, then this must of course be equal to the Eulerian quantity at the position R as a function of R naught. Okay, these identifications need to be done to get the two quantities, uh, to compare these two quantities. And basically, these two approaches are equivalent, or of course they should be equivalent. It depends on the situation which description is more convenient, or which is handleable in an easier way. Uh, in principle, these two approaches are equivalent. Okay, now we have introduced this, the Eulerian and the Lagrangian picture. Now the next point we are dealing with is the time derivatives. What are the time derivatives in these two different pictures? Well, there are two time derivatives, of course. We can define in a Lagrangian way the time derivative, and they are usually denoted by the total d by dt, whereas the Eulerian time derivative is usually denoted by del over del t. What does it mean? Lagrangian, we always fix the initial position. So the Lagrangian d by dt time derivative has to be taken at constant initial value. So this is the co-moving observer time derivative. And according to the Eulerian picture, we have to take this Eulerian time derivative at a fixed position, because this would be the appropriate definition of the time derivative. So, question, what is the velocity? Next, we would like to know what is the velocity of a flow within the flow. Which time derivative do we have to take, or are we free to define the velocity in terms of the time derivative? Can we take the Eulerian time derivative to define the velocity? What is the velocity? It's the time derivative of the position vector with time. So which one of these should we use? Can we take the Eulerian time derivative? Uh, pardon? Why should we take the Lagrangian one? Yeah, position is constant here. So it does not make to take the time derivative of the radius vector once we keep the radius fixed. That does not mean. So we can define the velocity only in terms of the Lagrangian uh, picture. Okay, so the velocity is given by the Lagrangian time derivative of the time-dependent position vector of our fixed mass element. Okay, that's one. So the question now is, what is the relation? We have now defined the velocity, and what is the relation between these two time derivatives? Can we transform, or can we get a relation between these time derivatives? And for this purpose, we consider the Lagrangian derivative, time derivative of some quantity f. So we calculate d by dt of the quantity f in the Lagrangian sense. So if it's Lagrangian, then this f should be in the Lagrangian framework, and this f, I have dropped now the indices. It should be the Lagrangian one, which depends only on the initial position and time t. Okay, now we know that we can identify this Lagrangian f with an Eulerian f. Go back here. F of R0 and t is actually equal to the Eulerian quantity at the position r, which corresponds to R0 and t, comma t. Okay? So we do this, or we use this identification, and here we switched from the Lagrangian to the Eulerian one by using the identity f Lagrangian at R0, t is f Eulerian at the position r, which belongs to the initial position r0 t, t. Now we have switched from the Lagrangian to the Eulerian description of f. Now let's do this time derivative. The time derivative still has to be taken at constant initial position. Well, according to the usual differentiation rules, this is the partial derivative of now the Eulerian quantity partial derivative of f at constant radius. So this is the differentiation which comes from this part of the time dependence of the Eulerian quantity f. And then we simply differentiate this quantity f by the radius vectors in an Eulerian sense. Now we are in the Eulerian picture. This here the radii are the radius vector is the independent variable, and the differentiation of r with respect to time in the Lagrangian sense with r with constant r0. This is dri, the radius vector, the time-dependent radius vector, position vector, dri by dt at constant r0. Once I use here this summation convention, which tells once we have two indices occurring at the same time, we have to sum up over this index. So this is a sum over the i's. I dropped the sum sign. Is that okay? Do you agree? Okay. So what we got is d by dt in the Lagrangian sense is d by dt in the Eulerian sense plus simply these here are the velocity components multiplied by the gradient of the quantity f. So the final result then is the f by dt, Lagrangian, is the f by dt Eulerian plus velocity vector times the gradient of the quantity f. Okay, so this is the connection, or this is the relation between Lagrangian time derivative and Eulerian time derivative. They are different by a factor velocity times gradient of the quantity. Let's apply this immediately to the velocity derivative with respect to time. The velocity derivative in the Lagrangian sense of the velocity is what kind of quantity? If we differentiate the velocity in the Lagrangian sense by dt, pardon? It's the acceleration. Okay, so dv by dt in the Lagrangian sense, dv by dt is the acceleration. This is the Eulerian time derivative of the velocity field plus v times nabla times acting on the velocity field v. This is a simple application. Okay, I already said this which choice or whether you like to work with the Lagrangian picture or the Eulerian picture depends on which description is for the particular system more convenient than the other. Okay, let's proceed further to the final aim is to get the equations of gas or fluid dynamics. Yes? Suppose someone wants to calculate the Lagrangian derivative of velocity of a fluid element. Yes. So he just needs to take the total derivative of he will have the velocity function as a function of time and initial condition. Yeah, this would be the Lagrangian picture. The Eulerian picture is now I'm sitting on a fixed point and some fluid elements pass by and I see the velocity of these guys. Yeah, and there is a Lagrangian observer. Yes. And he wants to calculate the velocity. He just the velocity function, the velocity vector will be a function of time and the initial condition. Yes. And he just needs to take the total derivative of the velocity. Yes. A Eulerian observer who is sitting on the fluid element. Yes. He will take the partial derivative of the way he sees the velocity function that varies with time. He will take the partial derivative of that velocity function and that v dot grad, v dot grad thing and these two will be the same. Yes, they should give the same. Yes, exactly. So this means the left hand side v is like the Lagrangian v and the right hand side v is the Eulerian. Yeah, the left hand side is the Lagrangian acceleration, and the right hand side is the acceleration, which has the same value but written in terms of the Eulerian picture. Yes. So I'm talking about the velocity. The velocity of the fluid. The velocity of the fluid element on the left side, it is Lagrangian. Well, velocity can only be defined on the basis of the Lagrangian scheme. There is no way to define the velocity field on the basis of the Eulerian scheme. There we have to rely on the Lagrangian one. So velocity is, you have no choice. But of course, you can have a velocity field in an Eulerian description. And sometimes, well, to illustrate that, if you have, for instance, a shearing motion, like in a galaxy. In a galaxy, you have a gas flow, but on different circles, the angular velocity is different. So you have a shearing motion within the galaxy. And once you want to describe that in a Lagrangian way, then for instance, let's take, so you take a galaxy and on the various circles here, the angular velocity is different. So it does not rotate in a rigid way. So when one element starts here and the other one element starts here and it gets to here and this one gets to here, has a bigger angular velocity. So they are separated more and more, and even they can overtake each other. So this is a bad way to describe it in a Lagrangian sense, because then you get confused, because elements which are initially close to each other, they separate by a finite distance. In that way, it's better to describe it in an Eulerian way and to describe the velocity field at each point separately. You see this? It depends on the situation which you consider, whether Lagrangian or Eulerian is better. That clear? Does it answer your question? Then you would like to take a velocity field in the Eulerian sense. Yeah, shearing motion uh, are very bad for the Lagrangian description. Okay. Okay. So uh, we have now defined the acceleration and given the acceleration both in the Lagrangian and in the Eulerian description. Now let us go further to derive the equations of motion for a gas flow. We have to consider some additional theorems. Uh, the first one is Reynolds transport theorem. I will not go into the detailed derivations here, but I will just sketch what is done here. Well, in the Lagrangian scheme, we have a volume element. You consider a volume element which is given by dV0. It's given by the volume element generated by the initial position vector. So this is dr01 times dr02 times dr03. In the Eulerian sense, you define the volume element by the actual position, which is dv is equal to dr1 times dr2 times dr3. This is the way how to define volume elements in the two approaches, Lagrangian and Eulerian. The relation between the r's and r0s is given by the position vector, which depends the actual position vector in the Lagrangian sense, which depends on r0 and t. Now we have to, or the connection, now what we want to see is how are these volume elements in the Lagrangian scheme and the Eulerian scheme connected? Well, to get the DRIs as a function of the DR0 J's, we simply have to take the derivative or the DRs of this transformation. And what you have is the matrix of the derivatives of Ri with respect to drj times dr0j. Well, here again, we have to have summation convention. You sum over indices which occur simultaneously. Okay, this is a the simple differential form of this transformation. And we may now express dv in terms of dv0 by taking or by writing the functional determinant of this matrix in front of the dv0. That should be basic mathematical physics. You agree? Okay. Let's call this functional determinant J. And the question now is, or the Reynolds theorem now consists of determining the Lagrangian derivative of this functional determinant with respect to time. And what the Reynolds theorem says, dj by dt in the Lagrangian sense is equal to the functional determinant times the divergence of the velocity field. The proof is not very difficult. You simply have to differentiate this quantity here with respect to time and apply the properties of the functional determinant, which is total anti-symmetry, and then you end up with this equation. It's a lot of algebra which needs to be done, but it's straightforward, and therefore I would like to omit it here. It's simply differentiating this quantity, and you end up with dj by dt Lagrangian is j times divergence of the velocity field. So what happens if the divergence of the velocity field is zero? Then, of course, you see the functional determinant doesn't change. So this is constant. And what does it mean if it's constant? And we start off the with the volume element dv0. Then we start off with j equals 1. So if it doesn't change with time, what happens? dv is equal to dv0. So the volume element does not change between the initial conditions and the final conditions. That means the volume element, the volume of your mass element is not changed. And that means it is incompressible. Incompressibility is usually uh, written in terms of the divergence of the velocity field is zero. This incompressibility means the volume, your volume doesn't change, and therefore it's not compressed or decompressed. And you have to keep it separate from another uh, property which is always which is many times confused with incompressibility. This is homogeneity. Homogeneity means that the gradient of some quantity is zero. It doesn't that the quantity doesn't change from place to place. For instance, you can have a um, a homogeneous fluid means the density of the fluid is constant. Then the gradient of the density is zero. Uh, Incompressible is something different. You can have an inhomogeneous flow and an inhomogeneous, incompressible flow. So if you follow a single element, it might move to another position where it finds another density, but its own density or its own volume is not changed. So incompressibility and homogeneity are two different issues. Please don't confuse them. Always, or sometimes, once I dealt with homogeneous configuration, people said, "Oh, that's incompressible." It has nothing to do. You can have a homogeneous, for instance, consider a star or stellar model, and you compress it, a uh, very crude stellar model having constant density. Then you can compress it by keeping the homogeneity, but it's compressible. The volume of your star of a stellar model changes, so it's not incompressible, it's compressible, but it's homogeneous. The density gradient is still zero. So please do not confuse these two terms. Divergence of velocity field equal to zero means incompressible motion. Okay, now let's apply this uh, transport theorem of Reynolds. And for that purpose, we consider an integral quantity, a quantity which is defined as an integral over some density. So capital G is the quantity which is defined through an integral over the associated density over the volume. So in a flow, of course, the volume will change with time, and it is not trivial to differentiate this quantity, for instance, in a Lagrangian sense, because we would have to somehow to account for the fact that the volume of the element changes with time. So we cannot just take the time derivative and put it there because this integration changes, or the integration changes with time. The volume over which we integrate changes. So how shall we do it? Well, what we do, we transform first this volume. This is obviously done in the Eulerian sense. We transform this volume to the Lagrangian volume. So we write it, we transform it back. dV is equal to, where is it? dV is dV is equal to the functional determinant times dV naught. dV naught is independent of time, and the volume over which we integrate in the Lagrangian sense is independent of time. And then we can we can put the d by dt underneath the integral. Okay, so what happens? Well, this is already the result. Perhaps I should write down the one more step here. So the integral over the time-dependent volume of small g d by dt of this is transformed to the Lagrangian form. It's the integral over v naught g times j times d v naught. Okay, and then we can take this d by dt underneath the integral. This is integral over v naught d by dt g times j dv naught. And now we can we can transform the entire thing back. This is integral over v of t d by dt g times j dv. But this has to be done because this volume here depends on time. So we get the functional determinant here as a product to the density. And once we now use Reynolds transport theorem about the time derivative of the functional determinant, and we use the relation between the Lagrangian time derivative and the Eulerian time derivative, then we end up finally. Do you want me to show this in detail? It's with this step, I think you should be able to do it yourself. You you take the Lagrangian derivative from here. You apply the connection between or the relation between Lagrangian and Eulerian time derivative, and you use that the time derivative of the functional determinant is the functional determinant itself. Sorry, I made a mistake here. This is dv naught. You need another j here. This is 1 over j times times dv, because dv is equal to j times dv naught. So we have a 1 over j, and you use the Reynolds transport theorem about the Lagrangian derivative of the functional determinant. Then you end up with this result. So the Lagrangian time derivative of an integral quantity can be written in this way. So this is an integral over the Eulerian time derivative of the density plus the divergence of velocity field times the density. This integral, this volume integral, can be replaced by a surface integral according to Gauss theorem. So the integral over divergence, the volume integral over divergence, is the surface integral over the quantity. So this is the volume integral over the Eulerian time derivative of g plus the surface integral over the surface of our mass element of g times v times the normal vector of the surface element times df. So this is a consequence, this form is a consequence of Reynolds transport theorem. We'll use it now, or we'll apply it in the next step to, well, to the quantity g being equal or identify the capital G with the mass m, and the small g with the mass density rho. So this is mass and mass density, and we apply now this theorem which we derived to the case mass and mass density. We want to have that our fluid element will conserve mass. That means the m by dt, if we identify capital G with m, the m by dt is 0. This is simply an expression for mass conservation, and we'll see what the result will be. The m by dt is 0. The m by dt by this the previous result, then G is the mass density, and this is the divergence of the velocity times mass density. Then we are left with dm by dt is d rho by dt in the Eulerian sense plus the divergence of v times the density must be 0. This has to be true for any mass element. That means this has to be true for any volume v of t. That means that the integrand has to vanish. And we are left with famous mass conservation equation or continuity equation for mass conservation. Either we have d rho by dt in the Eulerian sense plus the divergence of the mass flux rho times v is equal to 0, or if we rewrite the Eulerian d by dt by the Lagrangian one, then we have it's the simple relation between Lagrangian and Eulerian quantities. Then we have that the Lagrangian time derivative of density plus density times the divergence of the velocity is 0. So these are two equivalent forms for mass conservation, which are known as the continuity equation for mass conservation. So this is one of the basic equations we have to use later on for fluid dynamics. Again, if the divergence of the velocity field is 0, then the Lagrangian time derivative of the density is 0. That means if we co-move with the fluid and the divergence of the velocity field is 0, then the density doesn't change. Incompressibility means that the volume of the mass element is not changed. The mass, of course, is constant. Volume doesn't change. And therefore, if the volume doesn't change and the mass doesn't change, then the time derivative of the density has to be 0, but only in the Lagrangian sense, if you co-move with a fluid, not in the Eulerian description. Okay. Again, incompressible motion means that the Lagrangian time derivative of the density has to be 0, and this is exactly the case once we have that the divergence of the velocity is 0 and vice versa. Again, I commented on the point it has nothing to do with homogeneity. Homogeneity means that the gradient of the density is 0. These two, they are very well separated. Incompressible means divergence of velocity field is 0. Homogeneity means that the gradient of the density is 0. These two issues have to be kept separate. Don't confuse them. Well, mass conservativity has an immediate consequence. Well, the consequence is if we have a quantity defined by an integral over rho density times f. F can be an arbitrary quantity, and we want to have the Lagrangian time derivative of this integral quantity, then we can, due to the mass conservation, this is equal to the integral over the volume of rho times the Lagrangian derivative of the quantity f. You can easily convince yourself of this relation by taking the original by taking this result, by applying this result, and by applying the continuity equation or the mass conservation. But I will not show this in detail. If you like, you can convince yourself in a few steps that this relation in fact holds and is a consequence of the general Reynolds transport theorem and of the mass conservation. So we need this later on. So let's have a second application of Reynolds transport theorem together with mass conservation now, and consider the integral quantity capital G equal to the integral over rho times the velocity over your mass element. Well, this is the momentum of our mass element. Rho times V, uh, V, V times the mass is the momentum. And for a continuous configuration, we take the density times dV as the mass element. So we have the integral over the volume of rho times V, which corresponds to the momentum of our fluid element. Well, now we apply famous Newton law, change of momentum. Oops, somehow I switched to the other. Sorry, okay. According to Newton's law, the change of momentum, the time change, of course, in the Lagrangian sense, that's what we mean. Change of momentum is done by forces, and these forces can be separated into external forces and internal forces. The external forces, for instance, gravity is an external force or a volume force which acts on the volume, and this might be described by a vector field which describes force per mass. This is given here by the vector field F, and internal forces. The internal forces are described by a tensor or less academic by a matrix. So the change of momentum, well, this is Newton's law, the time change of momentum in a Lagrangian sense is given by the volume forces, or external forces acting on that volume. This is the mass element times the force per mass. This is a vector field. Gravity, magnetic fields, and so on may be considered as generating this vector field F plus a plus the internal forces. The internal forces have the property that they act on surfaces within our configuration, or with respect to a mass element, which act on the surface of the mass element. So, why is that such a complicated form? Well, they act on surfaces. This means we have to specify a surface. The surface is characterized by the surface element and its normal vector to it. So you can have the case that these internal forces have the same direction as the normal vector to the surface. This is, for instance, the case if you have pressure. Pressure is a typical normal, so to say, normal stress. So the stress acts in the same direction as the normal vector to your surface. So you have a surface, this is a normal vector, and the stress acts in the same way. But you can also have, and that happens in fluids often, you can also have a a force which acts in the plane of your fluid, if your of your surface. So we have forces which uh, these are the shear forces which go in the direction, not in the direction of the normal vector, or the vector characterizing your surface element. You have to make a vector which is not necessarily within the same direction, but somehow aligned to it, both normal stress and tangential stress. And this is described by this tensor or a matrix. How can you make out of a vector a new stress matrix. These are the internal forces. For instance, pressure within a fluid is a internal force and needs to be described by the stress tensor. Okay, well, we can transform this surface integral into a volume which is such d by dt Lagrangian acting on the quantity, an integral with integrand rho times f is rho times df by dt. We apply this relation on the left-hand side. Momentum change is equal to, this term describes the volume forces, and this is the divergence of the tensor. So we transformed the surface integral into a volume integral. This is a tension, the divergence of the tensor T, stress tensor T. Now, if this volume is arbitrary, result, rho times dv by dt in the Lagrangian sense is replaced by dv by dt in the Eulerian picture. That gives rho times Eulerian derivative of the velocity field plus v times nabla v is equal to the volume forces terms plus the divergence of the tensor. This is or Navier-Stokes equation for flow. Okay, usually Euler equations are those equations, is that form of this type of equation where the shear stress is zero. Shear stress means that the shear tensor or the form, it's minus pressure times the unit matrix. This is the case for the Euler equations. Is it clear what the stress tensor means? Why does it, if we want to have only normal stresses, if we want to exclude the shear stresses, then we have to have, well, then the direction parallel to the normal vector if this matrix is diagonal. Okay, if you want to have this quantity parallel to the normal vector, then it can only be a diagonal matrix. Okay, so and the quantity which is nothing else but the pressure. Okay, so if this is the case, then the stress tensor without shear stress is given by minus the pressure times the unit matrix, and the pressure divergence is then nothing but the gradient of pressure. The tensor will be that we have the pressure gradient, the tensor divergence is nothing but minus the gradient of pressure here. But this form also includes the Navier-Stokes equation, which includes shear stresses due to, for instance, viscous. Yes. Is it a convention to take negative sign for the first? Well, it's well, in some sense, it's a convention. Yeah. Uh, you have to select one. You have to define your the directions. Well, it comes from the fact that the normal, better the normal to the surface of your mass normal vector of the surface element points. You can put it in. You can make it point into the element, or you can make it point outward. In this convention, you have to take the negative sign. Okay, now we will no longer consider the Navier-Stokes equation just for completeness. This is the full set of equations. But now Euler equation with the velocity. So we take this equation with minus gradient p at this position and multiply it with the velocity. Well, you probably know what we now get. Of the velocity times the components of the velocity of the force field of the volume forces minus Vi times the gradient of pressure. You have to sum up over same indices. So this is a sum over indices. Right, the last term a little bit. This is rho times VIFI, and this one might be expressed as the minus the divergence of P times V plus P times the divergence of V. It's very simple rearrangement of derivatives. Now we integrate this equation over the kinetic energy if we integrate over the volume. So integral over the volume rho times V times dV by dt is the integral over that one. You easily identify this is the kinetic energy. And this here is, of course, needs to be some kind of energy. What kind of energy? Quantity P times V, which may be transformed into a surface integral. It's P times V times the normal vectors over the surface plus integral over P times divergence of V dV. Well, this is this is the change of kinetic energy, or the kinetic energy is changed by two volume. This is work done by the surface forces. So we are now going to consider the energy budget of which follows from our Euler equation. change of kinetic energy is given by the work done by the volume forces plus the work done by the surface forces plus, but it's some step before the energy balance. So let's consider the total energy. What is the total energy of our mass element? The total energy of our mass element is composed of the kinetic energy. We have an expression for the change of the kinetic energy. It's uh, integral over 1/2 rho, per mass element times the density integrated over the volume. So kinetic energy is integral over 1/2 rho v squared. Internal energy is given by integral over rho times the specific energy dV, where specific energy means energy per mass element. Well, let's consider the change of the total energy, which means the change of this energy is done by several effects. It is done by the work. It is or it's changed by the work done by two sorts of forces. It is done by it's the work done by volume forces. It's the work done by surface forces. And so it is changed by nuclear energy generation, where epsilon should denote the specific energy generation rate in our volume, and it can be changed by energy transport, simply by a heat flux going through our element, possibly deposing or taking off some energy. So this needs to be described by the energy transport, and F is the heat flux vector which goes through our for you. Um, I will repeat the main points here and then we will continue and hopefully then we will collect all the equations we need to describe uh, stellar fluid flow and stellar pulsations. Thanks. So if you have questions, please ask. Yeah.
So I have a question that in the description of kinetic energy, interpreted in terms of work done for a volume and from the volume forces and from the surface forces.
Yes.
So third term. So do we like to interpret the third or we have
That, you mean the leftover? So far is a leftover. You enjoy, well, what you have here, this is the force per mass element and multiplied by the velocity. So this is, so to say, this is the distance here. It's also pressure is uh, force per area. So this is force times some distance divided by time. So this is some kind of work which is associated with the surface. That's the only thing I wanted to show here. There are two terms. The kinetic energy is changed by two terms which correspond to work. This work here is that done by the volume forces or the external forces, and this term is the work done by the surface volume forces and this by the surface forces. And there is some other term. We'll come to that term if we consider the complete energy balance. So this is the change of the kinetic energy, what we derive directly from uh, Euler's equation. There is uh, no other no other physics going into that. It's just multiplying in the usual way the momentum equation with the velocity and integrating and then seeing what's left. And the next step will be we now consider the energy balance. That means we take into account not only the mechanical part, but also the thermal part by introducing the internal energy. Okay, so I have to ask for your patience until we discuss this part here.